So in today's class of mathematics, I am doing this chapter 1 with you all, that is vector spaces and subspaces. Okay, so this is a lecture 1 for you all. So let me start with it. Okay, now look at this carefully. Okay, vector spaces and subspaces. Vector spaces over a field. Okay, this is the definition which I will be giving you all. Okay, the statement: vector spaces over a field. Let V be a non-empty set with binary operation plus, this is addition, okay. V into V tends to V, meaning V, when you multiply two vectors, it is going to give you all a vector, okay, called as vector addition. Now this is called as vector addition, and together with an operation, this is what? Dot. So F field, when you multiply it with a vector, it will give you a vector, and it is called as scalar multiplication. Okay, next, moving towards the next page, continuation. Then V, this vector under addition and multiplication, this dot, is called a vector space over a field if addition and scalar multiplication satisfies the following properties. Okay, so this, it should satisfy the following properties, then only you can say it is a vector space over a field. Okay, so let me start with it. Now the first property is over here, which I have given it to you all, and I hope you all can see this clearly. So properties of a vector addition, plus, this is a plus addition. Okay, addition sign it is. So plus is associative in vector. V is a vector, that is x plus bracket y plus z is equal to x plus y plus z for all x comma y comma z belonging to a field. Okay, the second one is what? Plus is commutative in V, that is x plus y is equal to y plus x. Okay, for example, x comma y belongs to V, so it should be associative, it should be commutative. Okay, third one is what? You can take down, there exists 0 belonging to V, that is vector, such that x plus 0 is equal to 0 plus x will give you x. Okay, for all x belonging to V. Okay, x is belonging to a vector. Here 0 belonging to a vector is called positive identity in V. Okay, plus identity in V, that is vector space. Now next, you can take down the fourth one. I hope you can see this clearly. To each x belonging to V, there exists minus x belongs to V, such that x plus minus x is equal to 0 is equal to minus x plus x for all x belonging to V. Here minus x belonging to V is called positive inverse, plus inverse of x in V. V is a vector space. In short, V comma plus is an abelian group. Okay, is an abelian group. Okay, you can take down the properties which it is satisfying under addition. Next, moving towards the properties of scalar multiplication. Okay, now this is the properties of a scalar multiplication. Now a dot x plus y is equal to a dot x plus a dot y for all x comma y belonging to V, and a belongs to a field. X y belongs to a vector space, and this a belongs to a field over here. Now next, second one is what? A plus b into x is equal to a dot x plus b dot x. So what I have done over here, first let me tell you all about the first property. Okay, so here a dot x, okay, a into x, okay, into x plus a into y, okay, a into y here. Okay, for all x here, this your x and y, here your x and y belonging to a V, and your this a is belonging to a field. Okay, second is what? A into x, b in plus b into x, b into x for all x belonging to V, and for all a comma b belonging to a field. Third one is what? This a into b, okay, and x will be separate for all x belonging to, x belongs to vector, and a comma b belonging to a field. Fourth is 1 into x is equal to x for all x belonging to a vector. Next, moving So here next was a vector space V plus dot over F is called as a linear space over F and Fn. Okay, it is Fn. Okay, so where I reached? Okay, space over F, and F is called field of scalars. Okay, you all can take down this. Okay, continuation of that. Now here are the few examples of it which you all can take down. Okay, like R is a vector space over itself with respect to usual addition and multiplication of real numbers. Second one is this is a complex is a vector space over itself with respect to usual addition and multiplication of complex numbers. Third example is what? Let F is what? Filled, right? Be a filled, then F is a vector space over itself with respect to the operation of addition and vector addition and scalar multiplication denoted in F. Okay. Now V is equal to R. Next example is V is equal to R. Okay, real, and F is equal to complex. This is a imaginary part. Okay, field, and V is a vector is a real. Okay, so let X is equal to 1 and A is equal to I. Okay, so A into X is equal to, now what is X over here? The X is nothing but 1. Okay, into what is A? A is nothing but I. But I does not belong to real. Okay, so therefore R is not closed under scalar multiplication. Okay, and next is what? R is not a vector space over C. This is a complex. Okay, symbol. So you all can take down these few examples, and I hope you all are understanding them too. Okay, you all can take down. Now next example is consider R2 over R. Define vector addition and scalar multiplication on R2 as follows. In this, what you all need to do is let X is equal to x1 comma x2 and y is equal to y1 comma y2 belongs to R2. Okay, now define. I am defining x plus y is equal to x1 comma x2 plus y1 comma y2. Okay, here for y. So what is in place of x? What is there? X1 comma x2, right? And in place of y, what is there? Y1 comma y2. Okay, so x is nothing but this, then plus over here, plus is there, so put plug plus, and then this is over here, y is nothing but this. Okay, now this is equal to what? Basically this is equal to, so this is equal to what? x1 plus y1 comma x2 plus y2. Okay, and you all can take down this example. Next, moving further, so what you all are getting? Like this, x1 plus y1 x2 plus y2. Okay, you all can take down this example. Next, so let A belongs to real. Define A into x is equal to A into x1 comma x2. Okay, this is a bracket over here. Okay, there is a bracket over here. Okay, next, now this is equal to what? A into x1 comma A into x2. Okay, so now let us see the properties of addition in R2. Okay, so here let x is equal to x1 comma x2 comma y is equal to y1 comma y2, this comma z is equal to z1 comma z2 belongs to R2. Okay, here the value of x is given, y is given, and z is given to you all. Okay, next what you'll have to do is take x1 plus y1, okay, in one this thing, plus z. Okay, now this is equal to what? Now what is your x in the bracket, in the entire bracket? What was your x value? X1 comma y1, then plus what is y? Y is y1 comma y2 over here. Okay, and then put a bracket. Okay, as per the formula, plus z is what? Z1 comma z2 over here. Okay, now what you'll have to do is x1 plus y1, okay, comma x2 plus y2, then plus write it as it is z1 comma z2. Now we have opened the brackets. Now what we have to do is So now this is equal to what? We have opened the bracket. Now x1 plus y1, okay, plus this z1 we will do, comma x2 plus y2 plus z2, okay, over here. This will be in bracket, okay, this x2 plus y2 and then plus z2. Now what you have to do is x1 plus, now put this in bracket, y1 plus z1, comma x2, keep it out, plus then y2 plus z2, okay, then put a bracket over here. Now this is equal to what? x1 comma x2, okay, plus y1 comma y2 plus z1 comma z2, okay. Now this is equal to what? X plus y plus z. So in this what we were doing is we were checking the associative property, okay, and addition is associative in R2, okay. You all can take down the final statement, okay, and you all can start writing down. So next is what? So let us see the second one. Now this is for commutative property, okay. This is for commutative property. X plus y is equal to x1 comma y, x2 plus y1 comma y2. This is given, right? The value of x plus the value of y. Now this is equal to what? x1 plus y1 comma x2 plus y2. Now we can write this as y1 plus x1 also. You will get the same thing, right? Comma y2 plus x2. So this will be what? y1 comma y2 plus x1 comma x2. So this will be is equal to y plus x. So basically it is satisfying the commutative property as well, like x plus y is equal to y plus x, right? So it is satisfying the commutative property. Next, moving further, that is let us see the next property, that is 0 is equal to 0 comma 0 belongs to R2 is such that x plus 0 is equal to x1 comma x2 plus 0 comma 0. Now this how we are going to do is x1 plus 0 comma x2 plus 0 over here, okay. Now this is equal to what? Here what will remain is x1 comma x2 will remain, which is equal to nothing but x, and this is equal to what? 0 plus x, okay. Now it is also, this property is also satisfied. Now let us see the last part, that is abelian group, okay. Now x, since x is equal to this is bracket, so x is equal to x1 comma x2 belongs to R2. Therefore I can say that minus x is equal to minus x1 comma minus x2 belongs to R2, okay. If this belongs to R2, then this also belongs to R2, okay, is such that x plus minus x into minus x is equal to x1 comma x2 plus minus x1 comma minus x2, okay. Now this x, okay, x1 minus x1 comma x2 minus x2 is equal to what? You are going to get x1 when you are if you do minus you will get 0, right? So I will get 0 comma 0. I have written it over here, 0 comma 0 is equal to 0. So minus, now this is equal to what? Minus x plus x. Now basically what it is, R2 plus is an abelian group, okay. It is an abelian group and you all can write it down. So in the next lecture I will be doing the property of a scalar multiplication in R2, okay. I will continue some part in next class, okay. I hope you all have understood. You all can take down, okay, and try to understand, and thanks for watching.